Thank you, Anna, for that wonderful introduction. Okay, so a very good morning or a good afternoon or good evening to everyone, depending on where you are joining in from. Yeah, I was not supposed to give a talk initially, but Anna asked me about what I do, and I started rambling about gravitational waves, and I realized that this is something I'm very passionate about. And then it struck me that why not share this with all of you guys, something that I've been working on lately. So I'll start from the very basics and maybe build up to a little bit of technicality. And if you get lost, feel free to fall asleep. I won't mind because you're behind the screen. Anyway, so first of all, since we are talking about waves, you have to think what gravity is initial actually. So gravity is something that it was known from prehistoric times, really, because if you fall off a cliff, you'll die. So that was known to the early man, but nobody really thought about what it is and what is the reason behind it, or what is the mechanism at work behind gravity. There were many great philosophers who thought about it. They knew that there's something pulling you down, but why? Why is it pulling you down? Can we switch it off? Can we bring it under our control? And so on and so forth. But there was no proper answer available to them at the time. And then, okay, so yes, so this is just a sort of a joke, and it's a misprint. Basically, what I meant is dawn of the scientific method. So during the Renaissance, there was the revolution that once you think about something, which the philosophers already did, you have to verify it experimentally. You have to show that it actually happens. You just can't say, hey, this is what I'm saying, this is correct. You can't really prove anything. So this idea of proving might be very obvious to us today, but it wasn't back then. And there were many great people during that time, like especially Galileo and Brahe and Kepler. You must have heard about Kepler. These people put forth ideas which they could show experimentally using actual observations. And they contributed a lot to the understanding of motion as a problem, and also to the problem of gravity. I'm sure you are aware of what Galileo did and what Brahe and Kepler are known for, so I'll not go into the details here. But what is important here is Galileo put forth this theory of relativity, classical relativity. That means there's no actual, no absolute frame of reference. Everything is relative to each other. So then there was this person called Newton. I hope you have heard his name. I don't know if you haven't. I don't know. Anyway, so he was a mathematical genius, and apparently people say that an apple fell on his head and he came up with this equation, but that's actually not true. But anyway, so you know what the universal law of gravitation is. That was put forth by Newton, and in conjunction with his laws of motion, he was able to explain almost every phenomenon that was known at the time, like from planetary motion to the motion of the moon to any mechanical system on Earth. He was able to explain why it happens. But there were a few problems. There were a few phenomena that were discovered with due time, which we understood that could not be explained using Newton's laws. And those were the problems of perihelion precession, which is basically the rotation of the orbit of Mercury on the sun. And then there was the discovery of the constancy of the speed of light, which was not accounted for in Newton's theory. And according to Newton, the action of gravity was instantaneous and it could act via vacuum. And this was very disturbing philosophically, because how can I sitting here affect you in any way without any intervening medium? Because if you think about it, the common sense says that, well, I have to touch you to affect you. So this was a problem with Newton's theory. And then also the instantaneous action, which is just a consequence of the speed of light, constant speed of light. So anyway, then came this person called Einstein. I'm sure you've heard of him too. And he combined these two ideas of the constancy of the speed of light and relativity into something called special relativity. I'm sure you've studied those in your first or second year undergraduate courses. And the problem with this formalism was that it was only applicable in inertial frames. Like if you're moving in a frame which is accelerating, you cannot apply these laws to get meaningful results. So then he came up with the general theory of relativity, which was his genius. And there were some fundamental observations about nature he found, which helped him formulate this theory. I'll not go into how he actually went into formulating it, what were the observations, but this is what he got. I think you can see the equation. Yeah. Okay. So there's this equation G mu nu equal to R mu nu minus half G mu nu, so on and so forth. There's a lot of jargon, but what you need to know is the left-hand side, which is G mu nu, that actually just describes the geometry of space-time. And by geometry, you just need to know that it describes how you measure the distance between 2 points in a particular space. For example, if you measure the distance between 2 points on the surface of the Earth, that is not actually just the direct straight line distance, it's actually curved. So that has a different G mu nu than general flat space-time. Of course, I'm talking about just space, but this deals with space-time distances. And the right-hand side is the distribution of matter and energy in that space-time. So what this equation just tells you is the geometry of space-time is affected by how you distribute matter and energy in it. And consequently, the matter and distribution change or move on that space-time according to how the geometry is. And this was put forth very clearly by John Wheeler, that space tells matter how to move and matter tells space how to curve. That's all well and fine. I mean, this was remarkable at Einstein's time, it still is, but let's say this is very obvious. The problem is, not really the problem, the fun part is, what if this matter that is contained in T mu nu, what if it's moving in a periodic manner? If it moves in a periodic manner, that should be reflected in the in the structure of space-time itself. So let's say if I have two massive bodies moving around each other, they are moving, so that's periodic, and that means they will affect their local space-time. There will be a change in the local space-time, and that change will propagate outwards. Why will it propagate outwards? Because nothing can travel faster than light. So there's a delay of the information reaching us. So these periodic changes travel through space-time in the form of ripples. That means this measurement between two distances, that changes with time. And that is what gravitational waves actually are. I mean, gravitational waves don't travel in space-time, their space-time itself will change. So that might take some time to sink in, but this is what gravitational waves are. And why are we concerned with them? Because gravity reacts with matter very weakly. So we expect that these waves can be detected from much farther away in the universe than electromagnetic signals ever can. And also electromagnetic signals get very scattered due to intervening interstellar media, but this may not. And this might give us clues to possibly dark matter in the future, because there are some clues that dark matter might be interacting with gravity. So even though electromagnetic signals don't, we can see signatures of those through gravitational wave observations. So that's why they're important. Now the thing is, how do we actually measure them? So I'm not sure if you can see the other screen. Just give me a moment. I'll share the other screen with you. Yeah. Okay. So there are many ways to detect it, actually direct and indirect ways. The indirect way is if you have a binary system, like a binary pulsar. If they're emitting gravitational waves, we can show that gravitational waves carry energy. And if they carry energy, that means energy is being taken out of the system. And that means the rotating system will lose energy, and they may move closer and closer together, which might change their orbital frequency. And we can observe this orbital frequency from here on Earth, and try to back calculate how much was the loss of energy. And if that matches with our theoretical calculations of gravitational waves, then we can say, yes, gravitational waves are real and they are emitted. But this is a very indirect way of detecting them. The real interesting way would be to actually measure the change in the length of space-time as the G mu nu changes, as the metric changes, as we call it. So these changes, even for the most powerful of sources like black hole binary black hole coalescences or neutron star coalescences, these changes are of the order of the diameter of a proton, even a fraction of them. So you need highly accurate and sophisticated technology like which LIGO and Virgo use to measure these detections. I'll not go into how sophisticated these are. You can look them up on the LIGO website, and how they actually achieve it. It's a remarkable human feat. But the thing is, let's say I create an instrument, I get I know how to measure such minute differences, but how do I actually know those are gravitational waves? How can it not be a child just running around the lab and creating these disturbances? So we need to have a waveform, we need to have a template, we need to have an expectation that what should a gravitational wave look like. And for that to happen, we have to solve these complex rotating black hole or neutron star systems using Einstein's field equations to see that what is the expected waveform. The problem is these are 16 partial differential equations which are coupled. So it's natural, you know how difficult it is to solve differential equations. So it's nearly impossible to get a general solution for this. So the only way out is to have approximations. And as a first approximation, what people do is take the linearized approximation. They consider the background space as flat, which is here, intermunium, and they take a small perturbation on it of the metric, which is what gravitational waves actually are, which is much less than 1, that is much weaker than the background. And if you do the calculation through, I'll just skim through this, it can be shown that gravitational waves are transverse in nature and they travel with the speed of light. And they have two types of polarization. So if you have particles in a ring and the gravitational wave passes by perpendicular to it, there can be two ways of motion. Like there can be a plus motion as shown in the first row, and there can be a cross motion, which is the cross polarization. So these are all the basic properties of gravitational waves that you can find in the linearized approximation. But the problem is gravity is not linear. By the way, this is the equation that I'm sure you've seen from electromagnetism. That's a vector equation. Here's it's just a tensor equation where it tells you what the gravitational wave is in terms of the Green's function, retarded potentials, and so on and so forth. The problem with full general relativity is that this H that you can see comes in on the right hand side too. So then that means you cannot find a full clean solution of the problem, and then you have to resort to approximation techniques. So I have this paper which I was writing for my master's thesis, and you use some mathematical jargon and you ultimately reach an equation which looks like this. I need to share that. There you go. Yeah. So this was the equation I'm talking about. You can see that there's an H on your left side and there's also an H on the right side. So you can't just integrate a source and find what your gravitational waves are. So this is done by a special technique called the post-Newtonian approximation, in which you expand this in the form of a series in orders of V by C, because it's a small parameter. And by V, I mean the speed of the internal speed of the source. So if you have like the first order approximation, you'll get the linearized regime. If you go to V by C square, that's the 2pn approximation, you go to the higher corrections. And this involves a lot of complicated maths. There are some infinities coming in at certain points, but we use standard renormalization techniques to get rid of them. We also have to take into account the different regions, how far we are from the source, and so on and so forth. And ultimately, what we see is these calculations become very complicated. Till date, only up to 5pn has been calculated. That is V by C to the power 5. Yeah, exactly. So that has been calculated, but the problem is we don't know what higher terms are, and we don't know whether those even converge. For a series to make sense, it has to converge. But up to 5pn, the waveforms that we have received, we see that those match very well with the LIGO data. But the problem is, what if this series does not converge? What if this series is complete rubbish? What if this series makes no sense? It's just a coincidence that is matching. There are people now, theoreticians now working on this problem. They say that the first detection that was made in 2015, they challenge it, that it may not have been a gravitational wave detection. But some people also say that it may have been a gravitational wave detection, but it was not from a binary black hole coalescence, because the formalism that we used to reach a target template was incorrect in the first place. So this was what my master's work on. I was trying to investigate like what are the pitholes that this post-Newtonian formalism can fall into. And one of the main problems with these were when you're expanding in terms of V by C, what happens near merger? Near merger, the velocities are very high. They reach almost the speed of light. Then how can I say at that time that my series converges? I cannot, because I'll need higher and higher terms. And there might be some infinities in, let's say, in the 7th term, which I don't know. So those are problems that need to be looked into. We have found some other anomalies too, which I unfortunately can't share at the moment. But so yeah, this is what I'm working on. So it's kind of depressing that maybe this whole formalism theoretical approximation may have been incorrect, but there's just one little hope. The hope is you can solve these equations numerically on a computer. And the thing with this is, once you do the analytical approximation, you see that right at the end, just when they're about to coalesce, you see that the results match with the numerical simulations. So that is some confidence that, okay, no, this series does converge. So maybe it's not completely wrong. Maybe we need to just be more clear about in which regimes are they correct. And just to verify how accurate numerical relativity is, I did a little playing around myself. I took some data from some public catalogs. They have some research groups around the world have made public their research simulations. So I took them. I took the data of the initial masses and the initial spins of the two black holes coalescing, and I tried to predict what the final mass and spin would be using machine learning techniques. So I used some deep learning neural networks and support vector machines, and I got about a 99.5% accuracy, but even better accuracy have been obtained by other people. But this accuracy, what I'm talking about, is with real data. So numerical relativity works, and hence maybe post-Newtonian approximation works only up to the 5 p.m. order, but maybe 6 p.m. does not. So we just have to wait to see if that is how it is. So basically, I think I have some time. I think I'll stop because if I speak anymore, it will get very technical and some people might fall asleep if you haven't already. So thank you.
Thank you very much for this talk. And are there any questions? You can raise your hand or write in the chat. Okay, I think I have a question about your future plans. So what project do you think will take place in future, in the nearest future, and how this area going to be in some years maybe? So do you know any projects which are already going to be? Sorry.
Yeah, right. So basically, first of all, what we need is a lot more data. We need better how do I put this? Better detectors, a bigger network of detectors, and get more reliable data. Only then we can say that, okay, my theoretical predictions do match with what is out there. With just, it's like you're interpolating something very complicated with just 2 points. So I can fit 2 points with a straight line, with a sine curve, or with a very complicated polynomial function. But if you have a lot of points, then you better get a better idea about what model I should be using. So that is definitely one thing that is going to happen in the years to come. And the second is, till now, this approximation that I talked about, the post-Newtonian formalism, it works. It works very well for the data that we have. But it would be very exciting to see if some data comes which we know from some other way that it is actually a gravitational wave, but my series does not predict it. So that would mean this whole formalism doesn't work, and maybe something more interesting can be developed theoretically.
Okay, thank you.
Does that answer your question?
Yes, and maybe one more question, because this is the conference from CERN summer students, and can we somehow discover these gravitational waves in CERN? Are there any possibilities? Do you know?
Okay, not really, because we don't really have any other reliable methods or principles of measurement yet. Like the only principle that we're using right now is the measurement of the change in length, and hence LIGO is so famous and so successful in doing that. There's another thing that people are trying to measure is the angular momentum carried by gravitational waves. So if a passing wave has angular momentum, it might produce a twist in your detector. So that might be a way to detect gravitational waves. Those might bring down the size of my detectors. But on the quantum level, on the or at the about CERN, I don't really think there is any novel idea or novel principle that we can use to make a detection directly yet. Except, of course, if you can find a graviton, so that would be great.
Okay, thank you very much. Are there any other
Yeah,
questions?
I had a brief one. I just wanted to clarify. You said the system of coalescing black holes and such were with 16 coupled partial differential equations, and so the solutions of those are done numerically and so on. Do you think there is scope realistically for that to be exactly solved? Is that for an analytic solution to come through for that? Is that sort of on the cards at some stage?
I don't think so. From whatever I know, no. With a classical, even if you use a classical computer and a very complicated algorithm for it, it would take millions of years for a lot of using maybe a lot of computing power. It would be able to, you won't be able to get a general solution for it. As for direct solutions, well, there's a Nobel Prize waiting for it. So I don't think that's really possible at this stage. And what I feel is there might be a new theory coming in that might overthrow general relativity even before you're able to get a general solution of this. That might be exciting. So yeah.
Perfect. Thank you.
Yeah, thank you.
So thank you.